So we have this famous YouTube channel. We are getting monetized soon. Okay. So welcome everybody to this exceptional session of the Chilean probability seminar in this room that has not been nice with us for a while, but on the other hand, we have a great speaker today. So we have Nicolas Champagnat that will discuss with us about the Monge-Kantorovich convergence of penalized macroprocesses.
Thank you very much. I hope everyone hears me. And it's a pleasure for me to be here today and to give this talk. So this is joint work with two colleagues from Nancy, Edouard Strickler, who's a young researcher that was hired a few years ago, and Denis Villemonnet, that some of you know already. And so I'm going to, before showing you the slides, I'm going just to give two examples to motivate what I'm going to explain on the blackboard. And so let me start with the so-called Bernoulli convolutions. So this is a Markov chain, very simple Markov chain. Let me write. Yeah, let me write it. So it's just a recurrent chain where you simply take the previous step divided by 2 and add some random variable theta n, and the theta n's are IID, and take either plus or minus 1 values with probability 1/2, right? So very simple. And so doing that, well, first of all, you can observe that the interval -2 2 is stable. I mean, so if you start from this set, you stay in this set. And then, of course, this is an ergodic Markov chain, and the unique invariant measure can be checked here to be the uniform distribution on the interval -2 to 2. And of course, convergence to the equilibrium is quite easy to handle because you have a standard coupling. And so the coupling, let me write it down. It's very simple. You have, you take X and Y2 initial conditions, and then you set X0 equal X, Y0 equals Y, and you construct the two chains, Yn and Xn, using the same sequence theta n. And doing that, of course, it's very simple to see that there is a contraction, a normal Schur contraction between the two Markov chains, because when you make the difference, you cancel the theta n out. And so the asymptotic convergence is quite trivial. And using this, of course, you have convergence so in, let me call it Wasserstein L1 distance, which is also called the Monge-Kantorovich distance, to the unique invariant measure. So it's in law, of course, in distribution. Distribution geometrically when n goes to infinity. I'm going to come back to that in the talk, but it's just, oops, the standard thing. Okay. And so now the question I want to address in this talk is, first of all, a remark. You have convergence in Wasserstein distance, but you cannot expect to have convergence in total variation distance because, so very simple remark, if x0 is rational, then xn is rational for all n. And of course, it's the same if it's irrational. And so, of course, you cannot expect to have convergence to some distribution like the uniform one in total variation, because depending on the initial position, you can have singular distributions with respect to the uniform here. So then, convergence in total variation is not possible. So the question I want to address in this talk is, what if you add killing to this process? And so I write it too large. So let me just add a new line here. What if xn is killed with probability 1 minus p of xn, say, where p is some function at each time n. So in this case, you probably know that you can expect to have convergence to quasi-stationary distributions, that is, distributions stationary conditionally to non-absorption, non-extinction, non-killing. But then, of course, the coupling is something that deals about the process xn. But when you want to look at conditional distributions, of course, it's not easy to handle what's going to happen for conditional distributions. So that's the difficulty is that the coupling that is constructed here is for the unkilled process, actually. Okay, so this is one motivation. And of course, just like here, you cannot expect to have convergence to the quasi-stationary distribution in total variation. So instead, I'm going to consider convergence in Wasserstein L1 distance. Okay, so this is my first example. Everything is good for you. Then let me give another one, which is in continuous time, but it's more or less the same. So the other one is a piecewise deterministic Markov process. That is also very simple. And there are going to be the two prototypes for the criteria I will describe. So my piecewise deterministic Markov process is the following. I consider the stochastic process solution to this switched ordinary differential equation. So IT here is the environment variable, which belongs to make things simple, to 0, 1, say. And I assume that it jumps from 0 to 1 at rate, say, lambda 0, a constant, to be simple. And from 1 to 0 at rate, say, lambda 1. And so IT is an autonomous Markov process. And given IT, then you simply solve these ODEs with the vector fields F0 and F1. And so consider, for example, the case where F0 is just a matrix A times X. I've not said XT belongs to, say, RD. And so I can take that where A is a matrix. And for F1, I can take A times X minus A with a Hurwitz matrix So this is simply a matrix with all eigenvalues, all real parts, or negative real parts of all eigenvalues, right? And so in this case, it's known that there exists an inner product such that this quantity is less than this one, where gamma here is the minus gamma is the supremum of the real parts of eigenvalues of the matrix A. Okay, and so in this case, it's quite easy to see that the two vector fields are contracting in the following sense. So simply, if you consider one of the two one of the two vector fields, if you compute fi of x minus fi of y with inner product with x minus y, then it's smaller than minus gamma x minus y squared. And so in this case, you know that the distance, when the process follows one of the two vector fields, the distance between two solutions is decreasing exponentially fast with this rate gamma, right? And so again, there's a very simple coupling. Here it's a bit more complicated because of the environment variable. So it's independent coupling until yeah, okay. So the coupling, I'm making a coupling of the process xi and the copy yj, say. And so I make an independent coupling until I equals j. Then, so this is the first part of the coupling. Then take j equal I, and that's all. And so for this coupling, there's a time t0 is the time of coupling of I and j. And after t0, what you, sorry? Gamma here is the supremum of the real parts that are all negative. So gamma is minus. There's some. Yeah, so Rubik's matrices means real parts negative for all lambda. This is the definition. Well, it's okay. It's a terminology I did not know about as well. But Edouard Strickler says it's the name, so I trust Edouard. Ah, mais je n'ai pas réussi à l'allumer. Bon. So now from this, what you get is that once the two processes follow the same vector fields, what you have is that if you assume that t is larger than t0, what you have is that xt minus yt is less than e to the minus gamma t minus t0 times xt0 minus yt0. And so you have similar properties of contraction, but this time after a random time, t0. But still you have the same behavior of the process. You know that, so this is due to Benaim, Leborgne, Malrieux, and Zit. in 2000 something, 2012. There's a unique invariant measure. And using this kind of coupling, they are able to prove that there is exponential convergence in Wasserstein distance. So it's a similar picture, right? And in addition, a small remark. Well, let me write it just here. It's not long. If A, so the vector A that I chose here, so A here is a vector in Rd. If A is an eigenvector of A, then the interval 0A, so it's in Rd, right? So I mean the segment between the two vectors 0 and A is positively invariant for the process. So this is really easy to check. And so this means that the invariant measure, you can prove that the invariant measure is supported on this set, on this interval. So again, this shows that you cannot expect better than Wasserstein. You cannot expect total variation for the same reason as before, because you converge to something which is singular to the distribution of X if you don't start from this set. Okay, and so same question, what happens if there is additional killing to this process? This time with a killing rate rho. So this is my motivation. And so now I can start with the slides if there's no questions. No question? Okay, so I go. It's in RD. No, what I mean is that you see, okay, so the first vector, I said that the first vector field is making you converge to 0. And the second one is making you converge to A, right? And so what I say is that if, in addition, if A is an eigenvector of the matrix big A, then it's easy to see that if you start in the segment between 0 and A, you stay there. So this, and as a consequence, this gives that the invariant measure is supported in this interval 0A, right? So it's singular. It's not. It has no density. And so if you consider one realization of the process, which does not start from this interval, then you're never going to be precisely. You have 0 mass on this interval, and so you cannot expect to have total variation convergence. It depends on A. Okay, so there's, yeah, you can make a rotation, and you can, but you know the matrix A can be any matrix. So it also depends. It depends on everything, on lambda 0, lambda 1, A, and capital A. And so of course you can make some rotation to get A at say 1 of the, but then it changes the matrix A. And you can make also a time scaling, so you can remove one of the two lambdas there, but then it also changes the matrix A, right? So, okay, it's not really, it can be explicit. I don't remember if they give in the paper an explicit expression. I think it's computable. In this case, you can compute the invariant measure, but I've not tried. No more question? Okay. So now, what I want is that you keep in mind these two examples, because I'm going to come back to them from time to time in the talk. So let's start. Is it working? No, it's not. Yes. Okay. So very fast. let me just give you some keywords about why quasi-stationary distributions are interesting. So the typical situation where it's useful is when you deal with population dynamics with extinction, for which the stationary behavior is usually extinction. But of course, if you look at a living population, it's not extinct, and it may exhibit some stationary behavior, and quasi-stationary distributions are made to describe that. But of course, it has also other applications, so it's very important in metastability, and it's also used as principles to build efficient algorithms for molecular simulation in an algorithm that is called parallel replica algorithm. Okay, let me again be fast on that. And it's also related to the phenomenon that is known in biology as mortality plateau, where you have, if you look at on the right here, if you look at the death rate, so it's a population of Drosophila, and every day you count the number of deaths, and then you compute the death rate per day, and you plot that, and what you see is that it stabilizes to some constant value in many situations, and this is so-called mortality plateau. Okay, so this is just a few words of motivation, but I'm not going to say more about that. Also, a few words about references. So this is by far not exhaustive, but because I'm going to describe the total variation convergence and the Wasserstein convergence, let me remind some references about convergence in total variation of Markov processes conditioned to non-extinction. So I'm not going to read that. It's not. Maybe I can emphasize that there's this very old reference by Birkhoff, who is the son of the famous one in ergodic theory. And this is quite interesting because it's an abstract criteria of convergence of, yeah, say, semi-groups. But it's really well designed to deal with quasi-stationarity, and it has not, I mean, it's not so known. Okay, so, and then, of course, you have many, many names, and some of them, you know them quite well: Servette, Martinez, Jaime, Sylvie, Pierre Collet, Denis Villemonet, okay, and many others, Vincent Bancet, Bertrand Chloé, okay. Lots of people working on that. And in contrast, in Wasserstein distance, well, there are not very much works actually. So there are a few more in the paper, but these are the main references we found. So there's one reference that is not dealing with Wasserstein distance, and that is not in this list. It's a mistake. I'm going to come back to that reference. It's with Bertrand Chloé and Marie-Noémie Taille. And then building on this work, Denis Villemonet proposed criteria that are general for convergence in Wasserstein distance. And then on the same idea, you have this recent paper of Lucas Journel and Pierre Montmarché. And another point of view is the one of Pierre Delmoral, and there's this work with Emma Horton that is also dealing with Wasserstein distance. And William Ostafrin also. Okay. So let me just skip all that. So now I'm giving you the setting. I'm going to give a criterion for both for discrete time and continuous time process, because this is not a problem at all to extend the analysis in the two cases. So two fixed notations. I'm going to consider a killed process that is constructed starting from an unkilled one, right? So Yn is the unkilled process. It's living in some measurable space E, and I add to E a symmetry point, but Yn never visits this point. But there's a probability P of survival that depends on the state of the process E. And with these two objects, I can define the Markov chain Xn that evolves in E and the symmetry point. And the rule is simple. I put Xn plus 1. If Xn is non-extinct, then I put xn plus 1 equal yn plus y1 with probability p of xn. Otherwise, I send it to the symmetry point. Okay? And once it's in the symmetry point, it remains there. Bon. Now I'm going to assume that the time of absorption is almost surely finite. So I need some assumptions on P. I'm going to skip that. You can design many, many examples of assumptions. So tau d here is my extinction time. And now in continuous time, it's very similar. So I have a Markov process yt, which is unkilled. This time I have a killing rate, rho. And the rule is the same. I put xt equal yt until tau d, and tau d, I can simply define it as the first time where the integral of the killing rate becomes bigger to some independent exponential random variable with parameter 1 that I denote theta. Okay? So this is my setting. And now let me recall what is a quasi-stationary distribution. Okay, so the definition is here. It's a probability distribution, probability measure on E, such that if the initial value of the process, of the kill process, is distributed as alpha, then the conditional distribution at any time of the process given non-extinction at the same time is equal to alpha. Okay, so just a remark, because it's going to be important in the sequel, is that if you start from a distribution mu that is not a Dirac mass, if you look at the conditional distribution of xt given on absorption, well, it writes like that, like this quotient, and it's not the same as the integral of the conditional distribution started from a Dirac mass at x integrated with respect to mu, right? So this is the nonlinearity of conditional expectations. Okay, so now all this is very well. Now let me remind you what one of the criteria that we did with Denis Villemonnet on total variation, convergence of conditional distribution. So we have a criterion that involves two elements. First one, it's a conditional Dublin condition. So it's a coupling condition, but for conditional distribution. And the second one is a sort of Harnack inequality. So let me explain it. So the first, conditional Dublin, it means that starting from anywhere in the set, the state space E, if I look at the conditional distribution at time t1 given non-absorption at this time, then all these distributions uniformly on X are lower bounded by some probability, some positive measure that I denote as a constant C1 times a probability measure nu. And so this means that there are all these processes, regardless of the initial position, all these processes share a common part. The conditional distribution share a common part, and so it's a coupling property. And the second one is comparison of probabilities of survival. And so it writes in the following way: starting from the distribution nu that is given here, you nowhere you can survive much better than starting from nu. This is what is written here. So if you start from any x, then it's bounded up to some constant C2 by the probability of survival starting from nu, and this has to be uniform with respect to t, so for any t. Okay, and so given these two conditions, so actually these two conditions are equivalent to the convergence of the convergence in total variation of conditional distributions of the process with exponential speed and uniformly with respect to the initial distribution mu. Okay, so this was the remainder part of the talk. And now, okay, so these are already said about Bernoulli convolution, so I'm not going to repeat it. I'm just going to show you what may happen if you have killing in addition. So again, let me recall that we have this property for the process, the Bernoulli convolution process, started from two initial conditions, x and y, that you have contraction of the distance between the two copies. Okay, and so now let me define the Wasserstein Monge-Kantorovich distance. That is well known, so it's just a reminder. So what I denote by WD of mu and nu, where mu and nu are two probability measures, is the following. So D here is a distance on the set E that make this set Polish. And so it's simply the infimum of the distance between two random variables u and v, where u needs to have the distribution mu and v distribution nu, and I take any coupling, any possible coupling. And in the case of L1 or Monge-Kantorovich distance, so if here D is a distance, you have the so-called Kantorovich duality property, which simply says that this distance is also the supremum over all Lipschitz functions f with Lipschitz constant 1 or less than 1 for the distance d. So this is what I denote Lip1 of d. And you need to take the supremum of the difference between f of nu and f of nu, right? So the integrals. So for Bernoulli convolution, there's nothing, I mean, it's just immediate. You have the distributions of the process starting from any nu and any mu, have a distance in Wasserstein that is decreasing as 2 to the minus n times the Wasserstein distance between the initial distributions. So this is just a consequence of the coupling estimate, right? But of course, if you look at conditional distributions, well, it's not so easy. So that's the point of the talk. And let me explain what can happen if you choose, for example, as the probability of survival, P of x, if you take, say, absolute value of x over 2, right? So here, this is my P. So let me assume that, for example, okay, so what you need to know and to observe is that, of course, it's very bad for the process to be around 0, because then it's killed with very big probability close to 1. Now, assume I start from a point here, x0, close to 2. And now, what can happen? So I draw one theta, random variable theta1, can be +1 or -1. Say it's +1. So theta1 is 1. Well, what I do is that I divide by 2 and I add 1. So it makes me increase closer to 2. And now assume that I take as theta2 -1. Then in this case, this is close to 2, so half is close to 1. -1, it's very close to 0. It's very bad for the process, right? So there's a so-called death valley that the process has it's very difficult for the process to cross the death valley at 0 here. And so in this case, you expect, I mean, this has strong influence on the conditional distributions, because with this specific probability of survival, P of x, you can make explicit computations and see that the Wasserstein distance between the conditional distribution started from x and y is actually always lower bounded by 1/2 times the distance between x and y. So this is a case where, even though there's almost sure contraction of the path, due to the killing, you don't have convergence in a Wasserstein distance. It's just wrong. Okay, so there's a difficulty. It's not so easy as it looks, or as it may look. So this is the setting. I recall it once again. Maybe, yeah, okay. This is just to introduce some notation. So all this I already said, the first part. Yes. Well, the problem is that explicit computations are very difficult to do. So the case of linear No, it's because it's linear that you can make explicit computations. Otherwise, it's even stronger if you have x squared, then you expect that it's even worse. But I do not know, I do not have explicit lower bound. Yeah, so we designed this example just to have an explicit lower bound. And so, yeah, it's very specific, but of course, it's even worse if the Death Valley is even deathier. Yeah. Okay, so just my setting, I'm just going to use notations that maybe you're not very familiar with. So I'm using the notations of penalized Markov processes in the sense of Pierre Delmoral. So what I mean is that I want to express my conditional distributions in this form, and Z of t is a penalization, right? And so corresponding to my two cases, either discrete time or continuous time, you need to take this ZT, right? So in discrete time, ZT is the probability of survival at first step times second step until t minus 1. And so here you penalize the event yt in A by this probability of survival, and you need to normalize it because this is the conditioning part, right? And just a remark, you can write it as e to the minus a sum of rho of y I, where rho is the logarithm, rho is here, p is e to the minus rho, right? This is just to have consistent notations, because in continuous time, it's exactly the same. Zt is e to the minus an integral of rho. Okay? So this is my notation. Now, with this notation, I can state my main assumption that I call A. And so my assumption, there's something about the state space. So this is very simple, right? It's a first work, and it's just the basic case that we considered. I assume that D is bounded. So in some sense, I'm considering processes on some compact set. You may think of that because it makes things much simpler. And what is important is that the function rho, so the killing rate in continuous time and the logarithm of the survival probability in the discrete time, both need to be Lipschitz for this distance D. So this is expected, actually. Okay, and now the main part of the criterion is the following one. So this is something that writes this way. So I assume that there exists a coupling, a Markov coupling between two copies of the process that I denote yx and yy. X is the starting point of y, x, and y is the starting point of this guy. Okay, and so it writes this way. I take the expectation of the penalization of the x process, the process starting from x, times the distance between the two processes, and I normalize it. So if I come back to the initial notation, it's simply the expectation of the distance between the two paths, given the first one survives, and only the first one, right? And so I assume some exponential decay of this form for these quantities. So this is a property of about there exists a Markov coupling that satisfies this property. Yes. Okay, so this is my notation. So the y is the unkilled one.
Sorry. No, but
yeah.
Why?
Yeah. No, but these two are the unkilled. So the true processes are the capital X, right? Sorry. So this is my a bit tricky for notation, but okay, this is the way. This is why it's more convenient to write it with penalization, because you do not have to deal with the capital X process. We only deal with the Y process, the unkilled one, but penalized. Yes. Yeah, it is. So actually, we could have expected to have less. So okay, first of all, it's not strong because it may remind you. So let me come back a few slides before. If you remind of this condition here, this is really similar to this one, to the conditional Dublin. So here there's no coupling because it's only total variation. but it's exactly the same kind of property. You need to say that given X survives, there is some coupling. So in a sense, it's an extension in Wasserstein distance of this condition. And you can notice that we do not have any condition of Harnack type in contrast. Now, this is just intuitive in a sense, intuitive justification of this assumption. And indeed, we were not able to prove that it's necessary. Probably it's not necessary. But then what should we take as an alternative is not very clear. Maybe we could try ZT of YX infimum with ZT of YY. So it's a sort of symmetric conditioning, but it's not really easy to interpret probabilistically. We tried that and we did not succeed. Actually, we tried a lot of possibilities. And this one happens to work, but I do not have so satisfactory explanation of that. And so the conclusion of that is that with this assumption, we have what we expect, and that's the only assumption needed. We have that Wasserstein distance between the conditional distribution starting from mu and nu for any mu and nu decays exponentially with some positive rate beta t. And there's this contraction term here, which says that if the initial conditions are close, well, the convergence is better. Okay, so this, if you consider the total variation case, this is exactly what you would get with the total variation, actually. So this implies that there's a unique quasi-stationary distribution because you can take as mu and nu the distributions after some time t and some time s of a given process, and it's going to converge. And because my space is Polish for the distance d, there's some measure in the limit that necessarily is quasi-stationary distribution. So here's the main result. And just to come back to the previous example, if you look at the case where the probability of survival was the absolute value of x over 2, then it gives you the rho of x as minus log of x over 2. And of course, this is not Lipschitz, because at 0, it's minus infinity. So, okay, so it does not enter this theorem, and that's fortunate. Okay, so this is the main result. And now I can give ideas of the proof, or I can come back to my examples. Maybe let me try to give some ideas of the proof. So the first point is that the key point is that you have some semigroup, some non-linear semigroup that for penalized processes or for conditional distributions. So here it's simply, so stated probabilistically, it's simply you look at, so R ST capital T of f of x is just the expectation of f of x at time little t, starting from little x at time s, given non-absorption at time capital T, which is later, right? So if you let capital T be fixed and make vary s and t, well, this is a time inhomogeneous semigroup. And okay, it's written here. Now there's a point that I already say, but I say it again. If you look now at R0TT, well, it looks like it's similar to a conditional expectation that I want to study. So starting from a Dirac mass at x, it's just the expectation of f of xt, given it's non-extinct at the same time t. But of course, if you take a non-Dirac initial distribution mu, well, it's not the same because there's this nonlinearity. Okay, so now the steps of the proof are the following. So there are not so many, but this one is difficult, and I'm not going to explain it. So if you remember, there was an Harnack inequality in the total variation criterion that just disappeared. But actually, it's not. It's still needed, but only in the proof, because this property is implied by my assumption A. So this means that my assumption A is quite strong, actually, right? Because it implies very strong properties like this one, and this one simply says that regardless from where you start, X or Y, if you look at the probability of survival for any time t, well, it's always comparable up to some multiplicative constant. And this constant does not depend on t. So it's very strong, right? And this is a key point for the proof. So for example, it implies, maybe I'm not going to enter into this. Yes. Yeah. It's uniform on t, on x, and on y. So there's even no, usually you can have such properties. So usual Harnack inequalities for diffusions, it's on compact sets, right? But here it's x and y everywhere. So this is really strong. So my assumption A is strong. I'm going to say in the end some words about extensions, but okay. Well, I'm not going to, I think I do not have the time to enter into all the details of the proof. No, maybe it's not necessary for me to enter into this. One of the points, important points that then you can deduce is the following one, is that if you compare survival, so the penalization started from X and started from Y, well, you can prove that it's uniformly bounded by a constant times the distance between X and Y, and also times the probability of survival starting from one of the other or the other point. So the proof of that relies heavily on the Harnack inequality I mentioned before. Again, I think I'm not going to give the details. I could. If you're interested, we can discuss about that. And this point is the one that is needed to make the simple computation in this slide to work, which is the basic. So this is really the central step of the proof. Remember, I want to look at Wasserstein distance between conditional distributions. So the conditional distributions I'm going to recover by taking S equals 0 and little t equal capital T. So this will be in the end. Now I'm just considering this semigroup RST capital T with given S and T and see what I can do with that, right? So this is the first step. I would like to have, so these two quantities are probability measures. I would like to have estimates in Wasserstein distance between these two probability measures. So then I use the duality formula. I take a one Lipschitz function phi, and I test it with respect to these two measures. And I want to have estimates on that. Now we use the definition of the semigroup. And so we can decompose this difference into two terms. So in the first one, I keep constant the denominator, and I make the difference of the numerator. So it's exactly what is written here. And then I make the difference between the inverse of the denominators. And so it gives me, these quantities are bounded by the supremum norm of phi. And then I get this, right? And now you see why I needed to control these differences in the previous slide. This is just to control this term here. Okay, so the estimate of the previous slide. Okay, so why doesn't it work? Yeah, this estimate is just to control this. And for this, well, I'm going to use assumption A. So I'm going to say there's a coupling between these two processes. Oh, and I did it smartly. Okay, so I skipped one step, actually, I'm sorry. So here you can see that there's a penalization for X, and here is the same. So there's another term that I forgot, actually. Okay, where you have the difference between the two penalization, but it's of the same form as this one. Sorry for that. Now, if I take the same penalization, what I get is exactly the quantity I had in my assumption A, right? It's an expectation of penalization of x times the difference of phi between the two processes. Since phi is Lipschitz, I get the distance, and I have this Lipschitz norm here. And this is exactly what is needed in condition A. So then from this small computation, you can understand why we need this assumption. Now, the rest is tricky. The idea is, okay, now I need to modify the original distance because it's not going to work for this distance. So I need to spread it and make a cutoff of it with this d kappa distance. It's just technical. And for this distance, I'm going to obtain contraction results. If I choose conveniently kappa and the time t0 here, I'm going to have this contraction property that relies on this estimate, right? So it simply says that if I make time steps of t0 in my nonlinear semigroup, then I have a constant beta less than 1. I reduce the distances by this constant beta less than 1. And then the idea is to use the semigroup property here to iterate this and get some estimates in Wasserstein distance. Okay, this is just a sketch of the proof, right? So now from that, so there are consequences. So I'm not going to describe all these consequences because they are quite classical in the field. Okay, this consequence says that there's some asymptotic profile for the probability of survival. So Ex of Zt is the probability of survival. Well, it decays at some exponential speed, and then there's a limit here. Okay, so we have convergence under our conditions. I'm not going to say more about that. This other one is also quite classical. It says that if you look at the initial process condition to survive very long is going to converge when this very long goes to infinity to the so-called Q process. And so in this case, under our assumption, it's indeed the case. It converges to the Q process with some exponential speed. And the Q process has distribution Q of x that is explicit and that I've not written here, but it's quite classical. And this Q process also has ergodicity properties in Wasserstein distance that are inherited from the one I presented before. And last general property, it's quasi-ergodicity. So quasi-ergodicity is trying to have ergodic theorems for conditional processes, but of course it's not easy. And if you condition the process, then you cannot have L1 convergence as in the usual ergodic theorem, because you cannot compare the two copies easily. So then what we need to look is that define this mean ergodic measures, mu tx, that are simply obtained by penalizing the ergodic mean, usual ergodic mean, right? But there's this expectation here, right? Which is, I mean, we cannot avoid that, but it makes it less strong than the usual ergodic Birkhoff theorems. And then we also have convergence in Wasserstein distance of these ergodic measures to a unique probability measure, which is not the quasi-stationary, but it's just the quasi-stationary distribution with an additional weight, which is related to the probability of survival. Okay. So these are the main consequences, and now I can come back to my examples. So first example that I did not describe in the beginning is that actually, if you look at the previous works of Bertrand Chloé and Marie-Noémie Taille, Denis Villemonnet in the 2020, and Lucas Journel, Pierre Montmarché, basically the result that they obtain is that we can have convergence of conditional distributions when coupling is faster than killing. So what do I mean by that? Well, I assume that the coupling of unkilled processes has some contraction rate gamma, as before, as here. And then gamma needs to be smaller than the rate of killing. So more precisely, no, bigger, sorry, gamma needs to be bigger than what I call the oscillation of the killing rate. So it's the maximum minus minimum of the function rho, right? And so this is a general principle that was observed in the examples of these papers. And so with our criterion, it's just immediate. It's just trivial. If you have the uncoupled, if the unkilled processes contract with rate gamma like that, well, you simply put that in the condition A, well, you have the ZT in addition, but ZT you bound it by the supremum of rho, e to the supremum of rho, and then you need to divide by the normalization, and so you get the infimum and you get the difference, right? So this is just trivial. So that's nice because we recover these former results. We have versions that are a bit less strong, that are some sort of local, and that deal with the generator of the coupled process. So I'm not going to describe that, but it's related also to comparing the coupling rate and the killing norm. And now I can come back to the Bernoulli convolution. So actually what we can do is apply our criterion to the following extension of Bernoulli convolution. So I'm assuming that yn plus 1, the unkilled process, is just a random function f theta n plus 1 of yn. And the random function, so the theta n are still IID random variables, and the f theta are Lipschitz functions, and all of them needs to be at most one Lipschitz. And I call L theta the Lipschitz norm of f theta. And so then we have a result that if, okay, under the same assumption, also if the survival probability is e to the minus rho with rho Lipschitz, and if we have a small enough probability that the Lipschitz norm of f is equal to 1, so it needs to be sufficiently often strictly less than 1 in this sense, then we have condition A. So this works for the, of course, for the Bernoulli convolution very simply. And for the example, the PDMP example, so it's the same as the one I presented. Well, okay, I just assume that there's this contraction estimate, so I do not assume this specific form here. I just need to assume that, actually. Then I'm going to consider the distance. Okay, we can construct a distance. And for this distance, so actually this distance is going to be 1 if the two environments are different, and otherwise it's going to be the distance between the positions of the two processes. And I assume that the killing rate rho can depend on both components of the process and is Lipschitz. Then again, we can prove condition A, regardless on the value of gamma. So here contraction does not need to be strong, faster than killing. We need to have some contraction, and any contraction is enough. And so I have finished. Thank you very much for your attention.
Are there any questions?
You do the ratio of the absorption probabilities remain bounded below and above, no?
Sorry?
Like that the absorption probabilities starting at 2 points are bounded above and below, no?
Yeah, so in our other assumptions, so I can write it blackboard. So the condition A is that okay, let me use my notations, but which are And there's a, okay, I'm going to put that here. I need to normalize it this way. So if you want to make, how to say that, to make coarse bounds for that, then this you can bound it by e to the minus infimum of the rho, and e this by the supremum. And so this is, of course, this is this gives and this condition is, of course, quite hard to check in practice, because you have properties of the penalization joint with the coupling. And so this bound makes decouple things, but of course it's very strong, because we lose something, because we see in the PDMP example that actually we have something stronger than what we would get with this bound here. Yes.
Thank you. So in principle, having contraction is not useful unless it's faster than the.
So, but there's a general theorem that says that if contraction is faster than something, that's what we prove, and it's going to be okay. But we conjecture that actually, in many cases, it's enough to have some contraction and to control the bad events. So here, the bad event is that the time of coupling is large.
Right.
But here, in this case, it's possible to control it.
Yeah. So because in your proof, there's no explicit way to take advantage of some contraction.
No. So actually, our proof builds on that criterion, and then the main point is how to check this criterion. So actually, how it's written is not because, as I said, you have coupling of two elements that are jointly bound. Either you make some strong bound on this, and then you only have to look at that, or the converse. So in my examples, actually, so the first one, Bernoulli convolution, this distance is bounded pathwise by some by t to the minus n, and we need the distance. If you remove that expectation, so of course then it's just one. Very easy. And in this example, you have control, but only after time t zero. So here you have something that is related to t0 as well. So okay, it's a bit more tricky, but it's possible to check. Now, for general processes, checking something like that is not an easy task.
And one last question, a bit related to that, is that, okay, if you wanted to do, say, Wasserstein something else distance, Wasserstein 2, you would, I mean, it would be good to have an intuition of some underlying coupling here. So my question is, does this give you some idea of what could be a coupling, or it's not clear?
So you have exactly the point. So the problem of this approach is that we do not have interpretations of the coupling we obtain in the end. And so that's also why it's hard to formulate an assumption A that we could try, if we could formulate an assumption A that deals with coupling of random variables having the conditional distributions, this would be perfect. But of course, I mean, we do not know how to do that. And if you think about the problem, it's more or less related to the fact that it's hard to have Wasserstein distances between measures that do not have the same mass, because when you normalize, do not have the same normalization actually. So that's a big problem, and we would very much like to have this interpretation, but we don't have it. So it's one of the limitations. We need to understand things
and balance
better.
Okay, thank you.
To model, how you try to model this for some one-dimensional dynamical systems transformation.
Yeah, you mean, yeah.
¿Cómo se dice tonta de la tienda? De tonto.
Par exemple,
where the forbidden region is some small interval, things like that, and when you can iterate for one and for zero and one different two type of tonta transformation, and so there you will have some a very good a geometric a geometric forbid a geometric P, ray P or something like that. That is to say, it is not to know which type of P satisfies your conditions, things like that. Because since it will be geometric, I think perhaps it would be interesting.
So that's indeed very good. So we have not tried. So okay, what we did. So in the criteria we obtain, there's this assumption that the where is it? Yeah. So it's okay. It's random iteration, but here we assume that the Lipschitz norm is less than 1. So this is very restrictive. So in your case, it's not less than 1, but still you have good ergodic properties of these guys, of these iteration maps, iterated maps. And so that's really, that's really something we would like to do. But so we have some criteria that I've not presented, but they are not satisfactory for the moment. And it's also related to the compactness assumption. So there's another line of work where we are trying to use Lyapunov estimates out of compact set and only have local version of A. So this seems to work for the moment. And I wanted to say something more, but I forgot about your question. I forgot.
No, good enough. Thank you.
Thank you.
So any more questions? So if not, yes. So if not, we have to run. No. So if not, let's speak it again.